Hej och välkomna! And from now it's English. Welcome to the presentation of the robotics project. It's been going to be presented in English. I leave the presentation for the project leaders and pool leaders this year. Just to tell you that this will be recorded and later put on some web service to be played whenever you like, to go back and forth and enjoy what they have presented. So that you know that, well, it's going to be them that is visually recorded, but the sound in the locality will be. Then I leave the room for Ayub. Please.
Hello everyone, my name is Ayub and I'm the financial manager and the PR for the projects. I will introduce you to the outline. First we're going to present the course, the projects and our work, and then we take a break, 10 minutes. Then we go and ask questions. And after that, if you want to hang with us and go to the lab and see our workplace, you're welcome. This is the team of the year. We are basically 27 students from robotics and embedded system. 4 of us from embedded system. The course is 30 credits and it's 1 semester. Also, this course is basically you're able to practice what you have learned in the past 4 years in each competence we have, like electronics, programming, and you're able to build our own robots from scratch, or maybe continue with it with some older one. We design, construct and program the robot, so we build a complete advanced robot. This year, because we are many students, we have 4 projects. These projects are basically to solve realistic problems, not just like to have fun, it's more, it has something to work with. And it's also it's for research and industry. We have 4 competence pools because we are many, so we are divided in 4 groups: electronics, mechanics, AI, navigation control, signal and image processing. This is the workflow, how we communicate with each other, the examiner first, and then we have project managers. This is me. I contact with the project managers, the examiner and the pool leader, and also with companies and newspapers. And we have pool members that contact the pool leaders if they need anything. We use our tool to communicate. It's Microsoft Teams, where we chat and we assign meetings and make notes, and also create channels for each project or pool. We store files, documentation. Also, we can update that online. For you students who are going to work with this next year, you have all the files you need in Teams, so just take a look at it. And also it looks like this. As you see, it's our general channel. Like we have Henrik, he's posted about the meeting today, and we have other channels for the other projects, and here we assign meetings and files and chat with each other, so it's a good tool to work with. And as a PR, it's a new role for this year. You have to communicate with companies, you have to market the project, you also have to be in events, you have to seek events and make sure that people know about us. Also, you have to ask for sponsors. For example, we received a bike for the Autobike project for 17,000 crowns, and we got it for free. Also, contact newspapers, make announcements, and invite companies. For example, I've invited companies this year to present if they have thesis work. That's how we got contact between the students and the companies. And also, as a financial manager, you have to create a system that can save the orders you make for purchasing. First, we used emails and it did not work very well because the sequence changes. And then we use this Excel sheet on Teams, and you can update it online. You can define some rows you want, like date, items, and like full project, whatever you need to have to see. And I leave these are sponsors that we have connected lastly, and it worked well for the constructions, mechanical parts. We have saved a lot of money, and also we got a lot of components and parts we needed. I leave next project manager. I'll let you.
Yeah, thank you, Ayub. So now it's the fun stuff, the projects. So we start with my project. I was project manager for Project Autobike. You've probably seen the bicycle running in the hallways and stuff. So it's an autonomous bicycle platform for validation of traffic safety systems. We have Virt Electronics and also Chalmers as collaborators. So about the project, it's a joint venture project with Chalmers, and we're about to build a fully autonomous bicycle platform. And that means it should be able to balance, navigate, and obstacle avoidance. And the bicycle platform is a great educational platform, since you, like for us robotic students, it's basically involves almost every part of our program. Applications. Main application would be validation of safety systems in cars and trucks. And that was the idea from the start, but then as we went along with the project, we realized other applications is very real for the bicycle. So we have, it can be used for transportation, in bicycle rental services, even rescue operations and wild exploring missions, since the bicycle is a very thin body and can move around very freely. And maybe pizza delivery also, who knows. So for this year, we didn't get much from Micke to work with, but the goals for this year would be to get the balancing control on the bike, but remote control heading direction, so we could steer where we wanted to go. And navigation should be implemented if there was time, which we all know there is not. So what did we do? Here we can see the bike before. We got the bike from Cycle Europe, as Ayub mentioned, and we got it from free, front wheel drive, which was unfortunate. We realized too late, since all research has been done on rear wheel drive on bicycles, since that's the normal case for bicycles. But what did we do? We started absolutely from scratch. We didn't have a bike, we didn't have anything. We installed appropriate sensors on the bike, IMU for detecting leaning angle, and a steering motor to control steering. We also hacked the system on the bike to control the motor on the front wheel. We also did simulation in Gazebo, which is a simulation tool for Linux. And yeah, did we actually balance? So I have this video. See the supporting wheels? It's you get your expectations lowered, but we can look at this and see. Yeah. So it's not very stable, but this was the best we got. So we didn't quite balance it actually, but you see the steering works and supporting wheels work, and you know, yeah. So next year, what will you guys do? Or the fourth year student at least? there's a lot to do with the bike. For instance, like derive a dynamic model for front wheel drive. We can do torque control for the steering motor. Also, we didn't have brakes, which was maybe a problem when we ran in the in the entrance. No one got hurt. It's okay. We can do supporting wheels with the landing gear functionality, so you can pull them up when you're balancing. And maybe apply real-time OS. Maybe that also was a problem that it didn't balance. We don't know for sure. We had ROS on it now, robot operating system. And as I mentioned, maybe you also should reconsider the bicycle platform in total. Just start over from the beginning with a real rear-wheel drive, since that there are dynamic models for that available, so you can. I think it would be easier to do that, and also maybe smaller scale. Have this like foldable bike instead, which can it should be easier when it's smaller. Maybe build it in Lego, I don't know. So that was the auto bike.
So I'm going to talk about the Unicorn project. The Unicorn project envisions to streamline the handling of refuse in housing areas. The idea is to have autonomous robots roaming around and continuously empty refuse bins in these housing areas. Then it will carry the refuse away to a larger centralized refuse station. The project can be divided into 3 or maybe I can say 4 parts. Chalmers will specify the requirements for the system and also make a control tower to supervise all the tasks. Then we have MDH. We will provide the autonomous robot platform. We also have PVS and HIAB, which will design and construct the refuse bins, and also a crane solution that will empty the centralized refuse station and load a truck that can carry it away further for further transport. Then Göteborgs stad, which will provide a site for testing. And then we have Husqvarna and Volvo, which will assist us in all these tasks or work packages, we could say. It's a 3-year project. It will end in 2020. It started this autumn. And as you can see, it's a collaboration between industry and academia, both large companies and small and medium enterprises. So MDH's contribution: we will deliver the solution of the autonomous refuse handling robot. We will provide the design of the mechanical structure, the design of a safe and secure navigation system in an unsupervised urban environment. We will also design the sensor system for handling and sorting of the refuse, and the design of the communication system for the robot. So the goal for this semester, this period, we built a proof of concept autonomous robot that can navigate in a known indoor environment. And how do we get there? Well, we need to build mechanical structure design. We need to find the sensors that are appropriate and the computation units that can handle the data from the sensors. We need to implement a mapping and localization algorithm, path planning, object detection and avoidance. So this is what we started from. We have a Husqvarna Automower, which has support for ROS, has powerful motors, it can carry a heavy load. It also has wheel odometry, which we will use. And this is what we have built. We have put on a LiDAR, a stereo camera, an ultrasonic sensor system around the base of the robot. And we have, as a main computer, we have Jetson TX2. And we also manufacture a power distribution board to distribute the power from the batteries to all these sensors. And this is our vision for maybe the next year or 2 years after that. We'll roam around in the cities of Gothenburg. We have, as you can see, the new body design, and we also have the refuse compartment in the back, which will carry the refuse. So what is left? Future work. We need to further design the robot body and the refuse compartment, because it's not perfect yet. We need to find a solution for loading and unloading the refuse compartment. Now that is together with the PVS, which are constructing the bins, so that we can fit into that bin and then load the refuse. We need to also adapt the hardware and software for outdoor use, because right now we haven't tested the system outdoors, and we probably won't work. And also we need to construct a communication system. That is what's left for. And now it's time for Butler.
So, I'm Henrik and I'm project manager for Project Butler and the H at Home. It's not a humanoid, I'm sorry. It is a project which is a collaboration with Volvo Deepak MDH. It has been going on for a few years. We have support from Rollco, Mechanics and Beard. It is a request that we should build a robot that can run a robot cafe, and that contains taking orders, taking the dishes away, do all the stuff a normal waiter or butler would do. It's a 5-year project and we are in its 3rd year now. And we need to do it in compliance with the RoboCup at Home rules. And they are quite, even though we are doing this in an open platform, we don't have any hardware restrictions. We do have restrictions in form of size, attractiveness, annoyance, because you cannot really have something that sounds at 120 decibels at home, and you want something not a Hulk in your home. So we set up a goal this year. We got a case from our requester, and this is the first case we try to work to. We position the robot 2.5 meters from the table. It's gonna recognize a cup, go and grab the cup, back up, and then throw it in a trash bin. This might sound easy, but it isn't really. So for this year we had a sort of a new focus. We wanted to do a parallel platform, because it's been going on for 2 years. So we focus on hardware and software in collaboration with the Unicorn project. We aim to do path planning. There's also a collaboration with the Unicorn project. Trajectory planning for the arm. How do we grab it? How easy would it be to send commands to it? Object recognition, find the coffee cup, and reuse the intelligent gripper. So what did we do? After a lot of deliberations, discussions, we had this model drawn up with the unicorn as a base. So the lower body is the unicorn. Then we can work from 2 projects into 1. We save some time. We wanted to do a tower design, which is somewhat inspired by other solutions. We have the brain, the same as unicorn, a Jetson TX2 with ROS. The eyes are an Orbeck Astra Pro, which is an upgraded Kinect from a crowdfunding company. which sends its depth to IR and has an RGBD camera for recognizing objects. Also, we have CAN communication that goes down to a cortex that controls the motors, and then we get feedback from the motors, and we can do our commands fully. So we haven't done the complete assembly. We have tested all of these things: coffee cup recognition, CAN communication, path planning, trajectory planning, simulated and tested as parts. So they are now trying to assemble it in the final hour, see if it works. But if we look at what we did, I'm quite satisfied, especially with the CAN communication, which was a big hassle, and also the trajectory planning. They have a system set up for US fourth year students have an easier time next year. But some of the future work, there's a lot of future work. Some of the future work is movable head for the camera, so you can see stuff. The motors we selected, we couldn't get because of delivery time. So the motors upgrade, so we have suggestions for that. The gripper was not prioritized because we're short on time. And also for RoboCup at home, it's a different story. We would suggest that you do a pre-study if we need the long field or near field LiDAR to help you with the surroundings. It's also somewhat, you need to have human detection in that competition, because you need to see a human and interact with a human. And then it comes to the last point, human-robot interaction, and that's speech synthesis and recognition, because you're gonna give them commands. And that's for Butler.
Well, my name is David, and I'm the project manager for the project Swarms with the robot Naiad, which is a bit of a collaboration between several partners in different countries. And so, what is a Swarm project for us? Well, it is that we have an autonomous underwater vehicle that we're able to control, and the goal of that is to sanitize the sea floor from hazardous materials such as mercury or some other harmful substance. And what we want to do is that we want to map the surrounding area as well, so we can actually see where we've been and what that area looks like. And we also want to attend the Singapore Challenge next year, which is in March, where 13 different AAVs will compete. And so, what was our goal? Well, like I said, we wanted to map the seafloor, but we also wanted to combine that with a laser, so we project that laser pattern on the floor so we could see the contours a bit more better. And we also wanted a constant depth control, so we actually hover from the seafloor from 1 meter or something and have that constantly working. And also a simple mission planning, so it actually works independently. And what did we focus on? We focused a bit on the stereo camera, so we wanted the image processing and combine that with the laser. And we also wanted to have the sensor fusion, so we could have an accurate map. And what we had to work with was an IMU, which is for the acceleration and gyros, and the visual odometry, so we actually had some form of reference from where we were in the real world. We also wanted navigation and object recognition, which was for the competition more or less. So what have we done so far? Well, so far we have basic mission control, so we have the hover cruise control, and we can also have simple point navigation, so we can tell it to go forward and turn and such without the help of a controller or a keyboard. And we also implemented a simple, yet a bit crude Kalman filter. That was because we couldn't really implement the visual odometry just yet. So with the visual processing as well, we have a disparity map, so we can see the general shape of the bottom. And we have object recognition, which is for the competition. And as I said, the visual odometry is a bit limited, but that's because we had a bit difficulties with the Gimme 2 system that we had. And we also did some physical improvements. So we implemented a new battery compartment, which is watertight because the last one was leaking a bit. So that was good. And we also have a housing for the laser and a power distribution board for that as well, which can be interchanged with the waterproof ball dropper, which we also built, which is only for the competition. And the results, well, we implemented a simple controller, we have the power distribution, the Kalman filter, even if it is a bit crude, and object recognition, as well as navigation and the housing. So a bit of the future work for the near future is that we want to combine real images with the existing map that we got from the Kalman filter, because because we want to actually see how the surrounding looked where we were and such. And we also want to complete the requirements for the competition. That's not fully implemented just yet. And we haven't either actually attached the laser to the Naiad, so we need to do that as well. And then for the long foreseeable future, we want to actually implement real working simultaneous localization and mapping. Because right now we do it in steps, so we actually want to have it simultaneously working. But that's for the long future, and we also want to integrate that laser pattern with the camera, because it's quite difficult to see things when you're 100 meters down below in the water. And we also want to make it completely independent, so no human interaction at all. And that's more or less everything from the Naiad. I'll hand it over to the pools.
So yeah, now we will talk a little bit about what competence pools are doing in this project. We have 4 competence pools, and me, Martin, I am the pool leader of the mechanics pool. So, but what do? We basically do all the projects, just the mechanical parts of all the projects. So we do the design of all the mechanical parts, the things that you actually see. That's what we do. So first we do some sketching, and this is basically usually what our whiteboard looks like. A lot of really good drawn sketches, and we discuss what it should look like, and then we draw it in CAD, in SolidWorks. More a better drawing in SolidWorks to then construct the things we're doing. Then we also do some simulation, some stress tests in SolidWorks to see if the parts we drawn actually can have the strength to hold everything together, and also verify movement of the moving parts. And then the big one, the construction. We build the actual stuff, and we do that mostly in the workshop in Eskilstuna. We use the machines there. We use our CAD designs to mill the different parts, and then we assemble it with a lot of bolt and screws. So first, here are some CAD drawings that we've done in our pool. So as you can see, we have the butler and the unicorn as well. But so we did the design from scratch, and all the functionality with the lift mechanism, and we chose to have both the motors for the both joints here in the base here to minimize weight on the arm. And then we used some complicating cogwheel stuff here to move the arm, as you will see more later. And here we have the new battery compartment for the Naiad, which is watertight, and we have tested it and it works. And this is the autobike. We had to draw the autobike, the whole bicycle from scratch, because AI wanted to do some simulations on the bike, and we wanted a bike that looked like our bike. So then we had to draw the whole bike from scratch in SolidWorks. And this is the designs for the unicorn. 2 different designs. Yeah, 2 iterations, basically. So, construction. We do 3D printing, milling, drilling, lathing, screwing, sawing, metal bending, and purchasing. And then we assemble all of these together to build the robots. And this is a good picture, as you can see. Here we have some 3D printed stuff for the actuators. The actuators are not there yet. And then we have some milled parts here for the arm to be on. And these C-beams with linear ball bearings we got sponsored by Rolco, and also this screw for the elevator we also got sponsored by Rolco, so we had to assemble this together to build the robot. Here are some more constructions that we did. Better picture on the buckler, which we did from scratch, and the battery compartments. And here is the autobike, the front wheel steering. We had to mount onto the bike, and it had to. Yeah, the forces on the steering are quite high, so it had to be robust, and yeah, we're quite happy with that. And this is what we do inside, basically, with collaboration with electronics. We do all the mounts for the electronics and the breadboards and everything, so it can stay onto the robot. And this is a quick solution of a ball dropper that we got like 2 weeks ago. They said that we want a ball dropper, so we had to do a quick solution. We took some parts from the old Naiad, which was it was the Vasa. Yes, the Vasa. We took the gripper from Vasa and yeah, did a quick ball dropper solution from that. So that was a fun experience. So yeah, that's what mechanics do. Now, electronics.
Yes. What are we doing? We don't know what we're doing. So I'm Alexander, and I'm in the electronics pool. And I think what's been great about electronics is that we have had a real close collaboration between each member of the pool. Basically, what we do is read data sheets all day long now, but it's quite takes a lot of time to do actually, because you have to be sure that you choose the right components. And once you have done that, you can start manufacturing or designing the PCBs that you want to create. And then it's testing. Hopefully everything works, but it doesn't really do that. So you have to troubleshoot a lot to find out what's wrong with the things that you have done. So and there's also a lot of wiring that's you have seen on the bike, for example. That's a lot of wires. And you can also burn stuff if you're not careful. I've managed to do that 2 times. Maybe that's the record. Set fire on things. So basically, what we do is we sit down with the project leaders and discuss what do we want, for what kind of functionality do we want. And we would try to find the components and again reading data sheets to find out if the components match what they want. And what we use is Multisim and Ultiboard, or I've used Eagle also for the design of the PCB and also the schematics. And again, reading data sheets, I think it's funny. So for me, it's not a problem. A lot of things is that you need to have custom components, because even though there are a lot of ready components in the databases, there are still many components that doesn't exist, and you need to do custom components also. So you need to be sure that everything is correct when you and once you have done the schematic and the PCB design, it's time to do the milling. And I think everybody has seen a machine in the workshop that does the job. And then it's soldering. I think it's fun also. So one of the main problems that I've discovered, and I think most who've been working with electronics at least, is short-circuiting. Things are connected where not supposed to be connected. So that's one thing to check first, I think. Then you can check the voltage. It's one of the things that also need to be correct on everything. So that's one main thing. And also the functionality doesn't really perform the way you intended. A lot of designs aren't able to do you aren't able to do a simulation in, for example, in the software. So you really have to be sure that you've done the correct design, and then that's the functionality test proves what if that you have thought of from the beginning is correct. And also, if you have some type of communications, there are different protocols that we need to think of when we're designing. There are maybe some considerations when doing communication buses and so on. So that's all for me.
Hello, my name is Niklas. I am the pool leader for the AI and navigation pool. And these are the things we do in our pool. We control activation based on input. We plan movement and paths. We do object recognition, and we simulate the models. For the autobike, initially we wanted to start off with defining the dynamic model. It proved to be very difficult since the bike was front wheel drive, and we asked a lot of teachers for help, but no one was able to help us solve the problem. But we did suspect that it would be difficult, so we started quite early to develop other solutions to the problem. So we created a reinforcement learning algorithm to balance the bike, and we tested it in both the gazebo simulation and as well as in MATLAB simulation. And after verifying the algorithm, we were ready to test it on the real bike, and the results you saw earlier. Surely the unicorn, we use a ROS navigation stack, which consists of a move base with a cost map. And the robot starts with having the adaptive Monte Carlo localization, guessing wildly where it is in a static map that is loaded into the robot from start. And as soon as we give the robot a goal and it starts moving, it will start to realize that a lot of the initial guesses were very wrong. So after finding an edge in the room or a corner or something, it will make a good guess of where it is. And to avoid running into stuff, we have a 3-layered cost map. One cost map on the static map, which was there from the beginning. One layer on the obstacle map, which is constantly updated by the LiDAR and other sensors on the robot. And as well as one cost map on the sonar sensors for backing, since the LiDAR is looking forward. And to do the path planning, we use 2 algorithms. Dijkstra's for doing global paths, and timed elastic band planner to do the local obstacle avoidance. And the visual and wheel odometry is fused by an unscented Kalman filter. The butler, we have used a software called Move It, which is integrated into ROS. And we load the robot model, which is supplied by the mechanics team. And after some configuration, we were able to run the robot in simulation. So when we were able to do that, we felt we were ready to start interfacing to control the real robot. So we use ROS control to communicate over CAN. But we have not tested that yet, but hopefully this week we'll do that. And to see the cup, which was our initial scope of this project, we have used a stereo camera, an Orbeck camera, and we have trained an artificial neural network for roughly 20 days, and it can find the cups quite accurately. And when it has, we combine it with a depth map to find the XYZ coordinates of the cup. The swarms, or the Naiad project, was a bit overwhelming at first, since a lot has been done already. So we had to familiarize ourselves with everything. And once we got familiar with it, we realized there was some improvements that could be made. So we expanded the TCP/UDP communication between the different hardware that were there already. And hover control is done by controlling the thrust of the motors. And since the Naiad is naturally buoyant, we just increase the thrust to go lower if we are too high. Navigation is in place. We can navigate in the global reference frame, but with limited accuracy since the odometry, thank you, is very limited. Testing has been done in a pool here at school, in the swimming pool at Kristiansborgsbadet, and as well as in a pond in the forest at Häpplinge. And yeah, this project has been a collaboration with the IDT, the guys over there. So it's not only us students that has been working on this project. And we are currently preparing for the Singapore competition, and we want right now to be able to identify the frame that we should go through. Yep, that's it.
Everyone sound asleep? Yeah, we're almost done. Hi, I'm Arman. I'm pool leader for signal and image processing. Thanks, Carl, for the picture. So the last pool, what we do, we try to bridge the gap between the electronics pool and the AI pool. So it's mostly programming, but also working with electronics. And we try to actually, when the electronics integrates a component, we try to get the drivers running, we try to get the software running and everything ready for the AI to just take what the electronics gives them or give to the electronics what they want. So yeah, that's why we do image processing from cameras, we do sensor fusion and data acquisition from sensors, we do communication between devices if there's more devices in a robot, and we also built a couple of drivers for some components on the robots. So for each of the projects we did several things. For the autobike, we developed the remote control that you saw that was running. So one of the pool members did that, and we also did sensor fusion for the balancing of using the IMU. So there's more data that the IMU provides, so we used the data. And we also worked on the steering for the bike, the front steering that you saw. We did software for that, for the steering itself, and also for acquiring the data from the steering so the AI knows what position the bike is currently facing. Yeah, that's the bike. So for the Butler and the Unicorn, we did those two projects kind of together, if you haven't noticed already. I mean, most of the parts, and we also worked together with closely with the AI pool. So we didn't really we had like multiple people working together, even though they're from different pools. So we did motion control for that, for the Husqvarna. That was the base of the Unicorn and the Butler. And we did for the vision, LiDAR, and ultrasonic sensors, we developed like a software framework that works for both devices, even though they have different cameras and could in the future have different LiDAR sensors even. And in the vision we did point cloud and visual odometry, which are not both used on both devices but could be used. And we also have object avoidance based on the cost maps that Niklas has talked about. And specifically for the Butler, for the arm part, for the top part of the Butler, we did CAN communication between the nodes between each of the motors and their drivers to the base, to the Jetson, so that we could send like commands where to move. And we also made the control of those motors on the cards that are away from the Jetson. Yeah. And for the Swarms project, for the Naiad, we did TCP communication together with the AI pool. And we did image processing, which was getting images from one device to another and making point clouds so that we could have like a 3D map of the bottom, because the camera on the Naiad is facing downwards. And we also attached like a prototype, another camera that's facing front, like a small GoPro camera, similar to a GoPro camera, that would detect an object, or for the competition, like a gate that you would go through. So like we did color detection and object detection for the competition there. And I have an example here of the 3D map. So as you can see, the two pictures are left and right from the stereo camera of the Naiad. On the bottom there on the left is the depth map that was generated, the disparity map. And on the right there you can see a 3D map, a 3D point cloud generated from it. So you can see the rock that really sticks out. And then you get the data that it's close to the Naiad, so you'd have to move up to avoid the rock. Yeah. And that's it. Thank you for listening.